The examples that I showed you explicitly so far were done explicitly in 2D, so for the Cartesian and polar coordinate system in 2 dimensions. But the techniques and concepts that we have been using there, they also, of course, carry over to arbitrary coordinate systems. So, how to convert between coordinate system, how to get the volume element, how to convert derivatives, that you can also do for other types of coordinate systems. So I'm not going to do that explicitly anymore now for the coordinate systems that I show you. This is done part of the exercises. I will only now introduce to you the 2 most important coordinate systems for 3 dimensions. So the first coordinate system in 3 dimensions, that is actually a generalization of the polar coordinate system to 2D, from 2D to 3D, namely that the x and y coordinate are simply given polar coordinates, and the z coordinate is given still in the Cartesian coordinates. So the cylindrical coordinate system is to some degree a hybrid between the polar coordinate system and a Cartesian coordinate system. So how does it look? So if we have this point here in 3-dimensional space, then the height away from the xy plane, so the z direction, so that is simply given by the Cartesian coordinates. But the projection of that point on the xy axis, that is not described by x and y coordinates, but by the angle phi again and the distance r, so by polar coordinates. Now, such a coordinate system is again, of course, most useful if we have a system which has cylindrical symmetry. And for example, in physics, it's often used for calculating what happens if you have a cylindrical wire in the z direction and, for example, have a current flowing through it, then what kind of magnetic fields does it generate? Things like that. Now, because this cylindrical coordinate system is so similar to the polar coordinate system, it's also very simple to directly write down the volume element, because the volume element is then simply given by the volume element of the polar coordinate system for xy, which is r dr d phi, and then we have dz for the z direction. So you see it's very simple. The next coordinate system in 3 dimensions, which is a little bit more complicated, but actually more widespread used, that is the spherical coordinate system that I showed to you here. The spherical coordinate system, that is mostly interesting when you actually have a complete rotational symmetry around the origin in your 3-dimensional space. So the spherical coordinate system, the point in 3D space is defined by the distance from the origin, which is denoted by r. And then additionally, the angle theta that it makes, that this vector makes with the z-axis. And thirdly, with the angle phi that the projection of this point on the xy plane makes with the x-axis. So the angle phi is basically again like our polar coordinates, except now that the length r does not refer to the length r in the xy plane, but it's actually really the length from the origin to the point itself. So the r that we have here is not the same r as we have for the cylindrical coordinate system, for example. So we're using the same notation, but it's actually different. So this is, and I have to be careful about that here. Now you see that this coordinate system is particularly useful if you have something with a spherical symmetry. So because, for example, by specifying r equals a constant, we actually specify the surface of a sphere. Now, how do you now convert now between the spherical coordinate system and the Cartesian coordinate system? The only thing that we need to realize for that here is that what is the length of this space, of this segment here, and the length of that segment, we actually can easily see that it is the same as the distance of that point from the z-axis, and that length is given by r times sine theta, because, well, we have a 90 degrees angle here and the angle theta here, so trigonometry tells us that this distance here is r times sine theta. So we see that the x and y coordinates that we would have here they're simply given basically by now polar coordinates, but with this distance being given r times sine theta, so that in total I get x equals r times cos phi times sine theta, and y equals r times sine phi times sine theta. And the projection on the z-axis, that is again simple. So here we just have trigonometry that is given by r times cosine theta. Now, the inverse relations are now again a little bit more complicated, but you will recognize them from what we did before. Now the length is simply given by square root of x squared plus y squared plus c squared. So now that's the total distance from the origin. To get the angle theta, we need to invert this equation. So we need the inverse cosine, which gives us this expression. And for the angle phi that we have here, we get the same as for polar coordinates because, well, we have this additional sine theta here, but when we do this in the argument of the arctangent, the sine theta simply drops out. So this is how you convert between these coordinate systems. Now it's also interesting to think again about what is the volume element. And now here it's the most complicated of all of the ones that we've been looked so far. But as we'll see, it's actually not that complicated, actually. So what do we have? So for again, in the spherical coordinate systems, locally, when you change either the angle theta or r or phi, all these different directions are orthogonal to each other. So that makes it simple again. Now we only have to look at what are the length changes when I change either r or the angle theta or the angle phi. And for the length r, it's of course very simple because that directly is the length. That's simply given by dr. If we change the angle phi, then this arc length that we get here, if we change it by d phi, the arc length is given by d phi times the length that we have here, which is r times sine theta. This is a little bit hard to read. Let me just rewrite this. R times sine theta d phi. And the arc length of changing of this point when I change the angle theta is simply given by r d theta. And to get the volume element, we simply have to multiply all of these things together. And there we see that we now have dr times r sine theta d phi times r d theta, which gives us in total r squared sine theta dr d phi d theta. And that is the final expression that we have for the volume element. Now, it's good to remember these volume elements, and in particular, it's very important for these volume elements to remember that it's not just dr d phi d theta, but that you have, for the spherical coordinates, this r squared sine theta in front, or if you go back to the cylindric coordinates, we have the r that is there. So it's good to remember those and to memorize those because these actually come up often, and it's an easy mistake to forget about these additional factors here.